what are the basic blocks we're going to be using. These are random variables, expectations, and things like this. And from that derive probabilities. How are we going to do uncertainty computation? And so this is actually how can we compute this? Okay. So this is an overview over this lecture. So we're going to be talking about Monte Carlo methods. That's a method of computing integrals, actually, it will turn out. Okay. We look at other integration methods, quasi-Monte Carlo, Smoljak rules. Okay. Then we look at proxy models. So I'll explain what this is. That's kind of a model of a model. Okay. And some way of building these proxy models are interpolation, collocation. Another one is regression. So that's the part for this. And this is should make you ready for that in the third lecture. You will understand on how to use this practically. Good. So let's go back to our model problem. Okay. So we're looking at kappa or its logarithm, q, okay, as a parameter in this model, and this parameter was uncertain. Okay. There could be also more parameters. F and G could be parameters. So, but they could be control parameters. You may be able to control the rainfall. So it may be a smaller piece, which is porous material, let's say a sponge or something like that. Okay, you can control the experiment. You can control how much you put in one side and things like this. Okay, but you still don't know the conductivity, for instance. Let's say you do this in a lab experiment. Some parameters may be controlled, some parameters may be uncertain. Okay. So in a mathematical sense, they're all very similar. Okay. So let's call this a parametric system. So the system depends on some parameter, the action depends on some parameter. Okay. And as I say, some parameters may be controls, maybe this p tilde, and q may be uncertain. We model this in a stochastic way. Okay. What we assume is that we have a solver. Okay. So we can compute the state, which iterative solver doesn't have to be iterative, can be one which does it in one go. Okay. Given certain p, we can compute what the state is. Okay. And what this is going to be about is now, of course, u is going to be a function of p. Okay. If I change p, then probably u changes, the state changes. And so u, the state, is going to be a function of p. Now, of course, for a different p, if I want to get u, I have to solve this equation again. And when looking at this example, this may be a PDE which you have to solve. So it's not quite so cheap to do this every time. So that's why we want something cheaper. And that's called a proxy or surrogate model and or an emulator, okay? And then maybe we can use this in a lot of computations instead of this, okay? Later, I will drop this n for the emulator. Okay, but just now to make the difference. So this is the emulator, and this is what comes out of this here. Okay, it's exact. And especially later when some of these parameters are uncertain. Okay, this is the only point we're going to be looking at. Okay. Good. So this omega now, here we've seen we can look at random variables as functions on some set. Okay. And we now pick this up. So this is the set omega. And this is the set of all possible realizations, all possible ways of what this Q or the kappa can look like. This is the set omega. Picking one out, omega out there is one realization. That's to pick one certain connectivity. Okay. So for simplicity, don't think for them as a field for a moment. We'll come to that later. Think of them as just a vector of certain realization. So then that's not a continuum, but there's a discrete set. Okay, and the same for this here. Okay, good. So this is now the problem we want to solve. So it's an equation which has now become a random equation because there's a random element in there. And again, our goal are quantities of interest, which we saw before, where expected values of something which is like something like an integral over a certain subdomain, like the outflow on this boundary or something. So this is this guy in here. We've seen already, again, also that if we represent random variables as functions, then this expected value is also an integral. So the final thing we're interested in is an integral of an integral. Okay, One is an integral over the domain, the physical domain. Another one will be an integral over this space of all realizations, the set of all realizations. Okay. Good. So now just to give you a few, so what we'd like to know, of course, is now what is this U? What is the statistics of the state U? From that we can compute anything else, for instance, something like this. So we'd like to know the random variable Y. How can we describe the random variable Y or the random variable U? Okay. So this is called the forward problem, and the computing this is called uncertainty quantification. Okay. So there's different ways to get on there. Okay. One is this comes back to the question Angelica just had. So what do the moments tell us? So again, the moments characterize the random variable. One way of doing is to set up equations for the moments of this. Okay, so you set up what is U and what is U squared and U cubed and U fourth power and so on. Okay, or the same thing for Y. So what is the expected value of Y? What is the second power of Y and so on? Okay, what's the expected value? So what's the covariance and all this? These would be the moments. Usually this is only done when the perturbations are small, and this is typically done with perturbation. You use the mathematical tool of perturbing the equation, taking derivatives of the equation to derive these equations. Okay, so we will not go this way. Okay. Another way is to say I want to characterize these random variables, for instance, Y, through its probability density, and I set up an equation which describes how the probability density of Q is turned into the probability density of U or of Y. Okay, good. And for this, I have to set up new equations again, and they're typically called in chemistry, they're called the master equation, they're called the Fokker-Planck equation in other area. Again, we're not going to do this. Okay, what we want to do is that you can use your software, which you have already, to compute problems like this. Okay, so let's say you have a finite element program which will discretize this, or you discretize it with the finite element. You can solve this in an approximate sense, this partial differential equation. We're going to look at methods which can use this. Okay, one is direct integration. So one is to compute this quantity, this desired quantity of interest, okay, by a direct integration over the domain omega. We'll later turn this into another domain theta. Okay, and this is, for instance, via Monte Carlo, quasi Monte Carlo, or whatever. This is the first thing we're going to look at. And the other thing is to do an approximation. So it's to approximate this Y or this U as a function of this Q. Okay, so U is a function of Q, and we will approximate this. This was what I did before here. We will look at an emulator or proxy or surrogate model to approximate this. The same can be done with Y. Okay, good. So these are the general approaches. We will only look at these two here. So let's again look at the quantities of interest. Quantity of interest is something like this. Of course, this is a random variable because Q is a random variable, which makes U a random variable, which makes Y a random variable. Okay, and I can look at this as a function of Q, or I can look at this as a function of omega. Okay, and every time I'm computing a little bit of a different integral. Okay, good. And the thing itself is this integral over a piece of the spatial domain. Okay. Now, what I'm really interested in is the expected value of this. Okay, so I can take the expected value of this here or the expected value of this, and every time it will be a little bit different. Sometimes we write the expected value also like this with these angly brackets here. Okay, if there's just one thing in there, then it's an expected value. If there's two things with a comma in there, then it's an inner product. So there's different ways of writing the expectation. Okay, so what it is, for instance, we've seen this already. This is an integral with the ability measure, which is induced by this expected expectation, okay, which typically is computed with some density. Okay, we'll stay with this formulation for a second, okay, and we will approximate this by a quadrature formula. This is the numerical way of computing this integral. Okay, so you pick certain points omega z. These are the sampling points, the quadrature points. You evaluate this thing here. That means you solve the PDE for this omega z, which gives you a certain Q, which gives you a certain U by solving it, and it gives you a certain Y of Q. Okay, multiply by some weights and add it all up. Okay, that gives you an approximation to this integral. Okay, good. It turns out that if you really do it, there's quite a few omegas you have to look at. Okay, so to speak, remember we wanted to look at omega as a vector. And that's the dimension of the domain you have to take your integral over. It turns out to be a high dimensional integral. And this can be quite expensive to compute because there's many dimensions on one hand, and on the other hand, because the integrand is expensive. Every time you have to solve a partial differential equation, okay? And we'll look at both of these things on how to make this simpler, okay? Each evaluation is solving a PDE in this example, which I'm taking. Okay, the idea of the Monte Carlo method is actually quite simple, okay? It's a probabilistic method to compute this integral, okay? So you can trace it back sort of to the Comte de Buffon, who was a mathematician who lived 300 years ago. And this is, he had paper with stripes and was dropping a needle, and it turns out you can compute the number pi with that. You can look this up with Buffon's problem in Wikipedia. It will tell you how this works, okay? The next one who was using this more or less was Enrico Fermi, okay? But it earnestly started with someone called Stanislav Ulam. So Ulam and John von Neumann in Metropolis, they are all credited with inventing this. They were all working in Los Alamos in New Mexico in the United States, building the nuclear bomb, the atomic bomb, and the hydrogen bomb, okay? And this is where these extensive computations came up, and this is where this invented, okay? It's actually a little story he's telling how he invented it while he was sick and was playing patience with cards and was trying to compute the probabilities of winning. So what we do is we want to compute it like this, and the mathematical sampling method is to do the following. We randomly sample this, okay, with equal probability, which means with equal probability means that the probability of being in some set is equal to this probability which we've had before. That means we sample this according to this probability distribution. And then it turns out that the weights are all equal. They're all 1 over z, okay? So this is the Monte Carlo. This is simply explaining the Monte Carlo method. You sample the realizations, and then you add it all up and divide by the number of realizations. Okay? Good. So how does this method converge? First of all, it's a probabilistic method. Okay. So I've written this here too. So that's the result of our computation. I've taken the weights out here. Okay. And this is also a random variable because these points were random. Okay. So this, if you don't make no more assumptions than this variance of this guy is finite, then this converges in probability. It's a very key, weak kind of convergence. So the probability that the deviation is larger than epsilon goes to 0 as z goes to infinity. It's a very, very weak kind of convergence. And now you would like to know what is the probability, for instance, to be further than so many times the standard deviation away. And this is given by Chebyshev's inequality here, okay? This applies to all random numbers, this inequality, okay? So this is a random number to which it applies. This is its mean here, okay? This is what it is, the way I've denoted it here, the mean, the expected value. And so it's sometimes the difference can be the probabilities can be very, very sort of way off. It's not wrong, but it's very inaccurate, let me put it this way, okay? Because it applies to all random variables. Now, if we take the samples a bit more carefully, namely independent and identically distributed, okay? And then we assume that they have finite variance, then we can immediately say what the variance of this guy is. It's just the variance of these guys divided by z, okay? Because it's the sum, the average of them, okay? Then this converges almost surely. That means the probability that it converges is 1, okay? So it's much better than this here. Okay? And something called the central, so this was the law of large numbers, which tells us this here. The central limit theorem tells us that asymptotically, as z goes to infinity, this is a standard normal Gaussian random variable. So a Gaussian random variable, which is expected value 0 and standard deviation 1. So see, this is subtracting the mean makes it 0 mean, okay? And dividing by this gives it variance 1. And then by taking the normal distribution, we can compute much sharper bounds. than from Chebyshev's inequality, because now we know it's a Gaussian random variable. Okay. Good. So what are the advantages of doing the Monte Carlo method? You will see this later in the third lecture. The error and the speed are independent of the dimension. That's an advantage. Okay. All the other methods will see there is a dependence on how many dimensions you have. And it can very easily be extended. If it's not accurate enough, you just make more samples. Okay. And it's very robust. There's not much requirement on the function, on the integrand which you're integrating. So on this y of q, there's not much requirement on it, other than it has finite variance. Okay. But it is a probabilistic method, and what comes out here is a random variable. Okay. So for many things, this is not what you want. Okay. You don't want a random variable. For instance, let's say this thing is something which you need for your autopilot of a plane. Okay. Then you don't want it to be random. Okay. It's very hard to, not many people would fly with such a plane, I think, where the autopilot would use a random variable to do what it wants to do. Okay. So that's one problem, that it's probabilistic. That's an advantage on one side, but it can be a disadvantage on the other side. And the other thing is it's very slow. Okay. You can see the variance here of this. Well, you can see it here. It's this here. It's divided by the square root of z. So it converges like what the probabilistic convergence is like 1 over the square root of z. And that's very, very slow. Then when you look at the samples, they can be very patchy. They can leave holes, and they may cluster at certain areas because they are random. So, and this leads us to the next method. So what you see here, let me blow it up. So this is a Monte Carlo sample in this domain. Okay. And you see there's holes here, then there's patches where there's many, and these are many here, and there's very few here. So that's not really so good for wanting to integrate it. Okay. And people have tried to find other sequences, and what comes out here are sequences. These are deterministic sequences, and they give you something like this. Okay. And these are, I will not tell you on how it comes to. This comes from number theory on how to produce sequences. These are low discrepancy or lattices. Okay. And you see there's no patches, no clusters, and there's no holes here. Okay. So there's other sequences, but somehow they're also equal probability distributed. You have to require a little bit more of the increment. There has to be bounded variation. And you use the same formula as for Monte Carlo. You use this formula here. Sorry. This formula you say use also quasi-Monte Carlo. Okay. And often in practice much faster than Monte Carlo. And it's equally simple and equally extendable. Okay. But it turns out the error as this log z to the power d. Now one can do a few more things, make better assumptions, sort of stringent, more stricter assumptions or whatever, and you get close to this rate of convergence. 1 over z with a little bit taken away. Okay, so this is typically much better than this. So in practice, often these ways, these methods are much faster than Monte Carlo. Okay? So one thing which is important when you compute these integrals is to change the variables over which you're integrating. So remember the way I started here, I was integrating over omega. But I also can take this function, which I regard as a function of q, and I take this integral over the q domain. Of course, I have to integrate now over the push-forward measure. So this is the measure carried from q by q from omega to the q's. Okay, and I integrate over the q's. This transformation means that instead of sampling omegas in omega, I now sample q's in capital Q. And I use the push-forward measure. Okay. The problem is now what parameters, so what change of variables is really good to do it. Typically, these two are not really so good to do this. So typically, the given parameters, kappa of q, omega, typically are not good. So what is it we want from parameters so that they're good for integration here? Okay. So this means it's the same thing. It's choosing a basis in the space of random variables or choosing coordinates on the set omega. Yeah. We choose certain random variables which are good parameters. Okay. We want a good transformation. A good transformation is good when it's good for the integrand. And if we want the following, we want that this integral now, which is over a domain in Rd, because we're using d parameters to make these coordinates here, we want this to split into one-dimensional integrals. That's called Fubini's theorem in mathematics. We want to be able to apply this. And this is only possible if the measure here, this one here, is a product measure. So if this rho hat is a product of these rho j's here, then this is possible, okay? And it turns out then the random variables, the same as saying is that these random variables have to be independent. So what we want to describe the coordinates here, and we want to describe these functions in independent random variables. Then it's easy to compute these integrals, okay? So this is now a functional representation. We want to represent a function, let's say f, the original function f little o of omega, on some set omega would be our integrand, which we had here, for instance, this y cube. We want to represent it now in different coordinates, okay? Well, I think you've all learned on how to do this in analysis, how to change from one domain of integration into another one, okay? So taking new coordinates. Now, if you think back to this, if you've done this, just using any coordinates, it's very difficult to do the integral. If you have coordinates which are sort of wavy and things like that, it's very difficult to compute it. It's already better if you have coordinates which are locally orthogonal, okay? For instance, spherical coordinates, cylindrical coordinates, or whatever, they are locally orthogonal. It's already much easier to compute integrals. Okay? Or in 2D, the normal cylindrical coordinates are to the polar coordinates, okay? This corresponds to uncorrelated random variables, which when they logically orthogonal. Yeah? But that's not really good enough. We want independent random variables, and that means it's like the coordinates are Cartesian, and that we all know that's much easier. That's the easiest to do integrals in that, because then you can use Fubini's theorem. Okay, so we want a nice transformation into independent random variables. Okay, and then we want to compute this function f of omega as something like this. Okay, good. So we choose independent random variable, and then we will express this q in these independent random variables, and we can express this y in these independent random variables. And then we can compute our quantity of interest S, which is an integral now over these new random variables and their push-forward measure. But the push-forward measure we will choose so we know it, okay? And this drops into the one-dimensional integrals with push-forward measures, which we know because we can choose these independent random variables. Okay? Good. So once we've done that, we can use other integration rules. Sorry, let me stop here. The first thing is to know, you all know integration rules in one dimension. Okay. So this is now a one-dimensional integral, which you want to compute over just one theta, a real variable. Okay. And this may be the push forward of some other measure, okay? But we'll just look at this here, where you compute it like this. You have weights and you have quadrature points where you evaluate the function, okay? And that's your one-dimensional integral. Now, because we can use Fubini's theorem, we can now do this in every dimension. So let's taking the tensor product of this quadrature rule, okay? So the d-dimensional domain is the product of these one-dimensional domains, okay? And the rule for the d-dimensional, it's a little d up here, the tensor product rule with z points is to take zj points in every dimension, okay? And if you figure this out, what it is, it's just this here. You evaluate the integrand at these points, okay? And then take the product of the weights of the one-dimensional rules. And in dimension 1, it has Z1 points, in dimension 2 has Z2, and whatever in dimension D, it has ZD points. Okay? So that means that our integral is now computed as something like this here. Okay? So that's what it approximates. This product here comes from this product here of these functions, which we can do because these are independent random variables. They're Cartesian coordinates. Okay? Now we know how good is this rule? Well, we know if the function is smooth, the error can be something like this. So it can drop very quickly with smoothness, but unfortunately, when the number of dimensions is high, it makes it not so good again, okay? So it's dimension dependent, which comes out here. That is not such a big problem. The main problem is this, that very quickly you have a huge number of points, exponential in D, and that's what's called the curse of dimensionality. Just imagine you have a one-dimensional rule with 10 points, yeah, okay, and you have 100 dimensions. D is 100. Then you will have 10 to the 100 points here, where you have to evaluate the integral. That's a 1 with 100 zeros. That's how many times you have to evaluate the integrand. That's how many times you have to compute, solve the PDE. Now, of course, this is not doable, okay? So we want to have some rules which don't have as many points, okay? Two of them you have seen already. These were the Monte Carlo and quasi-Monte Carlo rules. But another rule is taking these one-dimensional rules and combining them in a different way. Combining them so that the grid is not full, the grid of approximation points is not full, but it looks something like this. In 2 dimensions, it looks like this. In 3 dimensions, it looks like this. And this is this recursive linear combination of one-dimensional rules, okay? So this is the rule with S points, and this is the rule with S minus 1 points. And you take differences of them, okay? And then you multiply this with a D minus 1 dimensional rule with these number of points. Of course, for this thing, you use, again, this rule of doing it, but then D drops another 1. And this way it goes all the way down to 1, okay? So doing this was invented by a Russian mathematician called Sergei Smolyak, okay? And this leads to sparse grids and rules which have errors which look like this in the number of points, okay? So it's only log Z and then dimension dependent. But this here, there has the net Z minus R. R was the smoothness of the function. So it has, the function is R times differentiable. So these rules, unfortunately, these rules, I have to say, they have negative weights when you figure them out what they are. And negative weights can be a problem. So these rules, when they work very well, but they may not work because of these negative weights, okay? They can give big problems because of these negative weights. They're not as robust as Monte Carlo, as quasi-Monte Carlo, okay? Good, so that was now one way of how we compute this integral by using this quadrature rules. Still the integrand, remember the integrand here, we're talking about the integrand here, is very expensive. Huh? To compute the integrand, we have to compute here our function u, okay, let me go all the way back here. So we have to compute, here I have it. So we have to compute u of q. That means we have to solve the PDE once. So it's very expensive to compute the integrand, okay? So what we're going to look now is proxy models. We replace the integrand, which is very expensive. We replace it by something, so I call the exact now what y hat. We replace it by a proxy meta or surrogate model. I will use the name proxy model, okay? Emulator is another name. So there has many names, this guy, the approximation. So the flow of computation, you can say, would be normally like this. You represent your uncertainty, then you solve the PDE, okay? That gives you u of omega as the random variable, okay? And then from this you get your quantity of interest, okay? And now we're going to replace q by some approximation, some proxy. We're going to replace u by some proxy, and we're going to replace y by some proxy, okay? And the rest of the lecture is going to be on how to construct these proxies, okay? So assume that this has been discretized by your favorite discretization method, assume finite elements, for instance, okay? So then this would be the nodal values. And now, because we have a stochastic problems, the nodal values are not just numbers, but they're random variables, okay? So they live in a space like this, Rn times the random numbers, okay? So it's n times the basic space of random variables. It's n random variables which you need to represent this, okay? Good. So we've considered direct integration. Now we consider computing first this here as a proxy model. Something like this here. So we want to approximate this un, each of these components, we want to approximate in some functions, okay? This is like in finite elements where you say, I want to approximate the exact solution of this PDE. Then we go back here. U of x, which is the exact solution of the PDE. I'm going to represent by nodal values times finite element ansatz functions. Okay, so now we do the same thing, but on the next level, we say, okay, each nodal value now, which is a random variable, we want to represent as some numbers times new random variables, okay, which are functions of our independent random variables, which we use to describe the whole problem. Okay? And preferably, we would like them to be also independent. Okay, that means they have to be in orthonormal random variables, in these IID random variables theta. That's the ideal thing, okay? And then it's easy to compute from u theta, then it's easy to compute y theta, and then we have a cheap expression for y theta, which can be used in any of these rules which we've seen before. Any of these rules here, where do we have one? Sorry. Quite a few. So in any of these rules, we can now use the cheap expression here. Okay, that will make the rules much faster, and then it doesn't matter that you have to use zillions of integration points if the integral is cheap to compute. Okay, good. So this will be done in two steps. First, we will pick a certain set of independent random variables, identically distributed. Okay, and then we'll construct these functions on that. Okay? Good. So the first step is this. I'm going now the historical incident to do this. Other things are possible. But the historical first thing was to express this in Gaussian random variables, called after Carl Friedrich Gauss. Okay. So how to find these coordinates, identical, independent, distributed coordinates on omega, which describe every function on omega. Okay, and then we want to have functions in these variables. The first thing to do is we take all Gaussian random variables, which are in this algebra of random variables. Okay, and they form a Gaussian Hilbert space, a Gaussian space, because the sum of two Gaussians is again Gaussian. And if you multiply a Gaussian by a number, it's also Gaussian. So they form a vector space, closed vector space, and we call this H. Okay. And now we will extract, which I abbreviate a cons. A cons is a complete orthonormal system. Okay, this is a cons. So how do you do this? Well, you pick one Gaussian, center it so it has mean 0, and then you scale it so it has variance 1. Okay, that's easy to do. Then you pick another one and use Gram-Schmidt orthogonalization. Okay, and so on. And then pick a third one and so on. Okay, until you've exhausted the whole space. So we can pick uncorrelated, because we make them orthogonal to each other and having mean 0. Okay, we can have mean 0 because we take the first one, the degenerate one, which is 1 everywhere. Okay, so all the other ones were orthogonal to that one, so they have mean 0 and they have variance 1. So that's why they're orthonormal. Okay, and they're all Gaussian. Okay, and they span the space. So here it's written once more, they're uncorrelated, and the mean is 0. If j is larger than 1, and only the first one has mean. Okay. Now for Gaussians, the nice thing is if they're uncorrelated, it's characteristic for Gaussians, then they're also independent. By the way, their measure looks like this. We know what their measure looks like. The push forward measure is something we know. Okay. But the nice thing, if they're uncorrelated and jointly Gaussian, then they're independent. And that means the measure of all of them, the forward measure, is a product measure. So it's just the product of these guys here. Yeah. And so I have to take a product of these functions over all dimensions. And I get the product measure, and I can use Fubini's theorem for integration. Okay. So now I have my coordinates. This is a way of constructing identically distributed independent random variables on my domain omega. Okay, so it's orthogonalization procedure. Now we want to find good functions here. So remember, we want functions psi alpha here with which we can approximate these random variables. Okay, so we found now the theta, the basic random variables, but they're not enough. Okay,
So now we want to find it. But with that, we know that these random variables, they are basis, an algebra, sorry. So for each Gaussian random variable, which we just constructed, independent ones, we look at their algebra, okay? And independent means if I take a polynomial from here and a polynomial from this algebra, well, then they're still orthogonal. So I have the hope if I take polynomials in these random variables, then I can achieve this. So I know I can achieve this. I just have to make sure that the polynomials in each of these subalgebras are orthogonal. So that's going to be the next step. So we're going to build a basis for this algebra. Okay. So this is the set of all polynomials in just this one random variable theta. Okay. We want to make them orthogonal to each other. Okay. Again, we take the first one to be the constant, and the second one to, so this has the number 1, and the one which number 1 with number 1 that's just the random variable itself. Okay. So this is constant. This is linear. Okay. And they are orthogonal to each other. So I have to start. And for k larger than 1, I take ck to be the orthogonal polynomial of degree k in this random variable, which is orthogonal for all the ones with lower degrees. Okay. So that this equation holds. So for L equals k, which means it has variance 1, and for KL less than k, the delta KL is the Kronecker delta is 0, they're orthogonal. Okay. So this way I get an orthonormal basis, okay, in this algebra, okay, of polynomials in the random variable theta. So if it's Gaussian, well, these polynomials are very well known. These are the Hermite polynomials. Here you have a picture of Charles Hermite. So these Hermite polynomials are the orthogonal polynomials in Gaussian random variables. But to have the whole algebra, of course, we can't just look at one coordinate. We have to look at all of them. So we need multivariate polynomials. So that's the next step now, okay, the third step. We build these multivariate polynomials. Sorry, I have to take a sip of water. We build these multivariate polynomials as tensor products of univariate polynomials, okay? So here the basis was labeled with a degree, okay? And now we want finite products in different random variables, okay? And we'll be labeling them with multi-indexes. Okay, so multi-index is a set of integers, okay? Because we don't know how many integers they are, we make them formally an infinite sequence of integers. But the infinite sequence is trivially infinite because only the first finite section is non-zero, and then it's just padded with 0. Okay, so for instance, we take this up to there, it's non-zero, and then from j onwards, everything is 0. Normally, this is like this. So the set we call j, and it's written like this. So it's all the infinite sequences with values 0, 1, 2, 3, and so on. Okay, this is the same 0, and this parenthesis around means it's only finitely many are non-zero. So there's a k, and for j larger than k, everything is 0. Okay, so from aj onwards, everything is 0. Good. So that means we can compute the length of such a multi-index. It's just the sum of all of them. Only finitely many are non-zero, and all the others want 0. So this is a well-defined sum. Okay, and now we define these multivariate orthogonal polynomials, as just products of this. So we take one such multi-index, and then for alpha 1, we take the alpha 1th polynomial in the variable j. Okay, so something like this here. So this is now a multi-index, and this is all of these random variables. And this for alpha j, we take the alpha jth polynomial in the jth random variable. And because most of these alpha j's, except for finitely many, are 0, and because this is 1, so this infinite product, except for finitely many, it's all 1. So it's well defined. Okay, and it's easy to see that the inner product, that means the correlation between these two, is this here, and it's just the product of these Kronecker deltas here. So they are orthonormal. Okay, and it's also easy to see if alpha is not equal to 0. The expected value of this is 0. Okay, now what we've constructed an orthonormal basis in our space of random variables. Okay?
as polynomials, orthonormal polynomials, and these basis random variables. And that's what's called polynomial chaos. Just have a look at this as an example. Imagine alpha is this here, 1, 0, 2, 5, and from then on is all 0. Okay. Then this polynomial is like this: is C1 in the first random variable, C0, because there's a 0 in the second random variable, C2, because there's a 2 in the third random variable, and C5 in the fourth random variable. And all the other ones have C0, which we know is 1s. Okay. And I've written it down now what it is. I've left this one out because it's a 1. And I know this one's linear, so I've written theta 1. So this is what this polynomial looks like. Okay. And you know, the length of this multi-index, you call this the total degree of this multivariate polynomial. Okay. And now when we look at all the linear combinations of these polynomials with degree exactly m, then it turns out it's homogeneous in this variable theta of degree m. And that's why it's called the nth degree homogeneous chaos. Okay. P0, of course, are the constants. P1 are the linear functions. So this is degree 0 homogeneous, this is degree of 1. Okay. And it turns, of course, because they're orthogonal to each other, that these subspaces are orthogonal to each other for n different from k. Okay. So the set of all polynomials we can write as a direct orthogonal sum of these homogeneous subspaces. Okay. That's called the polynomial chaos expansion, decomposition. Okay. And if we choose all these setters to be standard Gaussian, this is called the classical polynomial or just polynomial chaos. If the independent random variables are not Gaussian, and then we don't have Hermite polynomials, then it's called the generalized polynomial chaos. Okay? Good. So, and this, the first times this was used was by Norbert Wiener in the 1930s. Okay. And what he wanted to expand Brownian motion, or what's called today the Wiener process, in independent Gaussian random variables. And because these are random variables, he called this the chaos. Okay. Today, this is called white noise. Okay. Chaos typically means something different today, but we still just call this polynomial chaos because it's historically been called this way. Okay. Good. So, because he knew that the Gaussian random variables are an algebra of random variables, he used polynomials in Gaussians. Yeah. So, and this is Hermite polynomials in white noise. Okay. And this is what's the polynomial chaos. He stated that every random variable can be written as an infinite sequence of these polynomials. Okay. So the closures again, like the polynomials are their rational numbers. Now we want to fill in the real numbers. We take the completion, and then we get what's called L2 of A. These are all random variables with finite variance. They can all be approximated by polynomials, an infinite series of polynomials. These are the Hermite polynomials. It was proved later. This is the Cameron-Martin theorem. Okay. So this is today, this PCE is the abbreviation for polynomial chaos expansion of random variables is studied, and this field is called white noise analysis. You can also call it Hermite Fourier analysis because it's exactly the analog of Fourier analysis. So what do you use in Fourier analysis? You took an arbitrary function and look at its expansion in trigonometric polynomials. Here we take an arbitrary random variable and look at its expansion in Hermite polynomials. Okay, so it's exactly an analog to Fourier analysis, and that's why it's called Hermite Fourier or white noise analysis. Okay, so now assume we come back now to our thing. So assume we have discretized, let's say, a FEM system with this equation, or we can write it the residual being 0. Okay. So of course, we cannot compute with infinitely many random variables and infinitely many polynomials. We have to do something. So the first thing is we take a finite subset of these multi-indices. These will be their functions C alpha, in which we will do, or H alpha, which we were going to be working with. It's a finite subset of all of them. Okay. What we're going to be doing, we say we limit the maximum degree of each polynomial and each random variable. Okay. And we also take only up to position J and capital J, and when it's larger than capital J, they're always zero. Okay, so they have maximum length capital J and not more. Okay, so now we look at to express our input in such a polynomial expansion. Okay, and possibly the right-hand side, and then we want to compute U as a proxy model in this expansion. Then we can use U to compute Y and our quantities of interest. And you see now U, this is the vector of nodal values. If this was a finite element model, and each nodal value is a random variable, each nodal value gets expanded, and I've written this here in vector form. So this U alpha is a vector of length n. Okay. And if I look what this is here, so this has how many indices? It has J minus 1 indices from this here, and has one index from which position it is here. So it's a tensor, something with J indices, a tensor of degree J. Okay, so something which can be represented like this. So U is represented either as this or by this tensor. So different representations of this random variable. We will come later to see how this can be used to numerical advantage. Okay, this is next week. So similarly, we can represent the input like this, represented by this tensor. The load, if it's random, also by a tensor. Okay, and now the question is how to compute this here, which represents the solution. Okay, so how to compute this tensor represents the solution. Okay. So we'll look at two ways of doing this. Okay, so we just remember for each theta, this is a normal FEM system. Okay, so the simplest idea is to use collocation or interpolation. Well, let's solve this for a couple of points. Then we get U theta at these couple of points. And then after we've had this at a couple of points, then we use interpolation to interpolate between these points. Okay, so we take collocation points or interpolation points, and we at each of these points we solve the FEM system. So these are decoupled, what's called non-intrusive solves. We just don't use other normal form program to do this. Another one is projection, and this is to project this U of theta onto the subspace. We know this is on a orthogonal basis. So that means the coefficients can be actually computed like this, like in a product. When we go back to it, then we see that this is the expected value of this product, and that's an integral. And this can be computed by direct integration. Okay. And if we do this numerically, these are again decoupled non-intrusive solves now on the quadrature points. So let's look first at collocation. Okay. So this is what all of you know actually. So we solve this system for some point z, theta z, okay, capital Z points, and we get this here for each z, we get the solution. Okay. Now I rearrange this for each n, for each nodal value. I take all the z evaluations. Okay, all the z evaluations are put in vector. It's one vector of length z here. Okay. And then from the interpolation functions, I need the interpolation functions at these points for all interpolation functions. So that's something in this set z times n. Okay. And the coefficients, I again take for each n, I put them in a vector like this here. Okay. That's the vector of length m. Okay. So these are the things which I can evaluate. Okay. And now, what are the interpolation conditions of these? Because the interpolation conditions are this, that at the interpolation points, my interpolated value is the same as what I want to interpolate. Okay? And this is easily written, what I have defined before, as psi times Wn is equal to Vn. Okay? These are the evaluations that collected in Vn for each n, and these are the coefficients I want to compute. Of course, to be able to solve this has to be non-singular, so it has to be square, so Z has to be equal to n, and the matrix has to be non-singular, so not arrow points will work. Okay, that's one little problem with interpolation. Good, so it's particularly easy if the interpolating functions satisfy this Kronecker delta condition, because then the matrix is just the identity. Okay, and then it's very easy to do. One danger in interpolation, which you all know probably, is overfitting. If you have too many integration points, too many interpolation points, you start to get oscillations or whatever little errors in the evaluation of un of that zeta z get amplified. Okay, and then people often do, they take more interpolation points than unknowns, and then you have to do some kind of least squares regression. Well, that's a discrete projection, so we will look at that now. Okay. So what is discrete? We have more points where we evaluated the solution than we have coefficients. It's a possibly over-determined system. And we want to do what is we want to do least squares regression. So we want to minimize, I cannot satisfy this because there's more equations than unknowns. Typically, I cannot satisfy this, but I want to minimize the square of the error. In the appendix, I've made a little appendix so you can look at later. I assume now that you know, if you don't know it, it's in there on how these least squares problems are solved. Okay. We assume also that they are weighted. So at each point, there's a weight. So that this norm here is computed like this with some weights, capital WZ squared. Okay, they're positive weights. And we have a positive weight matrix here. If I put them on the diagonal of the matrix. Okay. So this leads now the normal equations, which come out solving this least squares problem. I have to solve equation here, which tell me this is an orthogonal projection, which is these squares. Okay, it comes out. I have to solve a system of equations like this. These are called the normal equations. Okay, and it turns out they look like this here. Of course, if the matrix is full rank, if the matrix is non-singular, I can peel this away. I get back to the system I had to location. CW is V. Okay, but otherwise I have to solve this system now. And what we assume here that Psi has full rank, and this will be true if these Psi alphas are linear independent. Actually, we choose them; they are orthogonal. Okay, and if they're not independent, you have to do something else, which is called Rule-Poincaré inversion, the pseudo inverse. So now we want to connect this discrete regression. This had nothing to do with our problem with spectral projection, and this will give us what weights to choose here. Okay. So we look at this spectral projection. It's called pseudo-spectral projection because it's done numerically. Okay. Good. So we know each of these coefficients of U theta can be computed by projecting orthogonally onto this subspace. Yeah? So we write it like this: is Psi beta times this here. Okay, this is the difference between what I want to approximate and my approximation, and we want this to be orthogonal to each other. So this is the orthogonal projection. But what is this inner product here? Well, the inner product is just the expected value of these, so this is this integral. Okay, so this translates into this, all these integrals being zero for any multi-index. These multi-integers have to be 0. Okay, so which means a matrix is going to appear. You know how to do this. This is what you do when you do finite elements. You take a span of finite element subspace, a span of finite element functions, and then you project the residuum actually onto that, and you get certain equations like this. So these are Galerkin orthogonality conditions. Okay? And the matrix which appears here, this is something like the mass matrix, you could say. Okay, and the right-hand side is given by this here. Okay, and then we get a system of equations to solve like this. By the way, if we choose these functions, as we said, we're going to do make them orthonormal, then of course, this is just the identity matrix. It's very easy to solve the system. Okay? Good. But now, if it's not like this and we have to compute everything numerically, then, especially the right-hand side, we have to compute numerically. So we approximate any function here by the quadrature formula. As we've done before, we've seen this on how to do this. Okay. So, and this quadrature formula now will give us the weights, okay? So the diagonal of these guys will give us this matrix, and it turns out then phi can be written like this. It can be written as this triple product. So the equations I have to solve for every n, this equation here, which I have to solve, actually looks like this. And now if you go back, this looks like discrete regression. So now this is a way to obtain these weights here. So the weights are just the quadrature weights of this quadrature rule. Yeah? And that's called pseudo-spectral projection. Okay? And if we take Monte Carlo, quasi-Monte Carlo points, well, then all the weights are equal. And the matrix W is just 1 over Z times the identity matrix. Okay. Good. So this is the same equation as for discrete regression. Okay, so we can view regression in an extreme case collocation. Yeah, remember, if Z is equal to N, then all these matrices are not singular. Then it's exactly just collocation, which we had here. Okay, we can see them all as approximations to spectral projection because this is really the best thing to do, orthogonal projection. Okay. Another way to find, so all these ways of doing it, they had nothing to do with the equation. Another way to say is we want the equation to be satisfied in some average sense. And this would be to apply Galerkin weighting to this equation, the residual equal to 0. So we want the weight the residual with these functions, with these ansatz functions which we're using. And we require this here to be 0. Okay, so this is the residuum times this ansatz function. We want this to be 0. Okay, and this will give us the tensor coefficients. So it will give us as many equations as there are coefficients here. Okay. I can write it all out in tensors, then this equation looks like this. So it's a huge system of equations. It's n times m equations. N for n nodal values and m for m functions here. Okay. And by the way, if you use Petrov-Galerkin weighting with delta functions, then we can recover collocation. Okay. Good. The Galerkin method, if we do it here very simply, gives coupled equations. So it seems like we need a new solver, a new software. But there's a way of solving coupled equations in a partitioned way, and then this is going to compute the residual by quadrature, and it becomes non-intrusive, and it becomes you have to sample the residual. Okay. So the difference between Galerkin methods done in this way and the ones we used before, here you have to sample. Here you have to sample the solution, and all the other methods as well, through the spectral projection. And here you have to sample the residuum. It's typically much cheaper to sample the residuum, but you have to solve this coupled way of equations. Okay. So this is the question of being or not being intrusive. Okay. Typically, you want to use your existing legacy software to solve this. You have a finite element program you want to use it. This is termed a non-intrusive equation. It only needs your normal solver. And this is clear for collocation, interpolation, and discrete regression. It's also clear for spectral projection in the numerically integrated form for pseudo-spectral projection. And the only question comes up with Galerkin, but it can be done with Galerkins also when you compute, if we sample the residuum. Okay. This, and I will not go further in it. I have 2 more slides in the appendix. You can look at it. I'll come back maybe next week to this. Okay. We will only be using these regression and collocation methods here in this course to compute this. Okay. Good. So let me sum this up. Okay. So the whole thing was about finding proxy models to compute these integrals and finding proxy models. Okay. First, we looked at computing integrals. Okay. So we looked at Monte Carlo, quasi-Monte Carlo, the tensor product rules, and the Smoljak sparse grid rules. Okay. But in their simple form, they had very, very expensive integrals. The integrand at each evaluation point was to actually solve a PDE, solve a finite element system every time. Okay, this may be okay if it's small and linear, but if it's big and nonlinear, that's not something you want to do. Okay, so that's why we want to replace our approximation to the solution by some proxy model. Okay, then the second part we looked at interpolation and collocation to do this, and that's often the simplest to do this, but it's the most unstable and dangerous. Okay, so these regression approaches are much more stable. Okay, and the regression in the form of pseudo-spectral projection is really the most stable in the sense it takes care of the background probability measure. This is where the weights come from. They don't fall from the sky. But all of these methods, they don't consider the equation. Now, if the equation is important for you and you want it to be satisfied in some weak sense, for instance, to be Hamilton's principle satisfied in some weak sense for all theta, well, then you have to use one of these Galerkin methods to solve the equation. And it's also possible in this way to preserve certain structures or symmetries which the solution has. Okay. For instance, if something's moving in time or whatever, time-dependent system, and it's a Hamiltonian system, you want to preserve the symplectic form. It's possible to do in this way. Not possible to do with these projection or collocation approaches. Okay, so this is the end of the second lecture. Okay, so we'll have now again a 20-minute break, and then Noemi Friedman will continue with her lecture. Is there any questions here? Maybe Bostein, you can switch on the microphones of all the people. If not, you can think of your questions. So, by the way, the slides go on, and I think you have the slides. So there's an appendix on these square problems. And these square problems relies on these 4 subspaces theorems, which I've written down for you. And I've written also down how to do Galerkin non-intrusive. Okay, so you can look at that. We'll come to this Galerkin non-intrusive, I think, in a later lecture. And this is just a reminder. I hope you know how to solve these squares problems. If not, we can talk about this next week. Okay, so you have a look at all these slides, and maybe next week, maybe at the beginning of the lecture, we take 5 minutes to take questions from this one here on Monday. Okay, so maybe on Monday we take the first 5 or 10 minutes to take questions if you don't have any. Good. Otherwise, if there's not any questions, I would log out so that the recording can be stopped. And then we'll see each other again on Monday at 9 o'clock. Okay? I'm waiting a little moment if there's any questions. If there's not, then I'll say bye-bye to all of you, and I'll see you on Monday. Okay? Okay, bye-bye.